Let us now talk about this question. We are given an array of integers. Every integer in this array appears even number of times, except two integers that appear odd number of times. So for example, there might be 100 integers that appear even number of times, and there are always two integers that appear odd number of times. There might be 100 even occurring integers, or 200, or 2, or 3, or 1, but odd occurring elements are always 2. You need to find the odd occurring elements. Let's see this example. So 3 is an even occurring element. It appears 3 times. 4 is an even appearing element. 5 is an odd occurring element. So 5 is an output. 6 also is an odd occurring element. It appears once. 7 is even appearing. So we do not print 7. So 5 and 6 are the only odd occurring elements in this array. In this example, there is only one even appearing element, but there are two odd appearing elements in this array. So our output is 15 and 16. So we can say that our input array size is always at least 2, because there are at least 2 odd appearing elements. Odd appearing does not mean 1. The odd appearing element might be appearing 3 times or 5 times or 7 times. Now please pause this video and think of a solution for this problem that works in theta n time and requires theta 1's extra space. Let us first talk about naive solution, which is theta n square. The idea is simple. We traverse through every element one by one using this outer loop. For every element, we count how many times it appears. So to count the occurrences, we have one more loop. So this part counts how many times array I appears, right? You traverse from j equal to 0 to n minus 1, and every time your array j is array I, you increment the count. And if count becomes odd, you print that element, right? So this solution prints the odd occurring elements. It has time complexity theta n square, and it does not use the fact that there are only 2 odd appearing elements. So we need to use this fact and need to come up with a solution that is theta n time and theta 1 extra space. It is strongly recommended to watch the previous video where we had to find only one odd appearing number. So this problem is an extension of that problem. We are going to use XOR again here. But you must be wondering, how can we use XOR to find the 2 odd appearing numbers? So our first step is same as the previous algorithm. We do XOR of all the numbers, right? So we find out XOR of 3, 4, 3 till 7, right? We do XOR of all the numbers. So let's call this as XOR. So what do we get if I do XOR of all the numbers where every number is even appearing and 2 numbers odd appearing? All the even number appearing occurrences, they will cancel out each other because x XOR x is 0, right? Now the 2 odd appearing numbers, they will not cancel out each other. So we'll get the result as XOR of 5 and 6 in this array. So I'm considering this array, right? And I am considering the XOR of all the elements in this array. So after I do XOR of all the numbers, my result is going to be XOR of 5 and 6. Now I have XOR of the 2 odd appearing numbers. How do I find the 2 numbers from their XOR? That's where this question becomes more tricky. We use one more interesting property of XOR to find the 2 numbers. If you do XOR of 2 numbers, x and y, then your XOR is going to have a bit as 1 when that bit is different in x and y. And your XOR is going to have a bit as 0 when that particular bit is same in both x and y. That's how XOR works, right? So XOR of 5 and 6 is going to have 1 when they are different here. It's going to have 1 when they are different here. It's going to have 0 when they are same, right? And all the preceding bits, because this is a 32-bit number representation, so there will be 29 preceding bits here, 29 preceding bits here. They'll all be 0 in XOR because they are same in both. They are both 0, 0 in both the numbers. So this is your XOR of 5 and 6. Now this XOR has 1 when the bit is different in 5 and 6. we use this idea. How do we use it? We take a set bit of this XOR. This is our XOR. XOR of 5 and 6 is this number, which is 1 and 2, 3, right? The binary representation of 3 is this. Now we take a set bit in this number 3 and we divide our all numbers of array into two sets. One set of numbers have this set bit as set and one set of numbers don't have this set bit as set. Let's explain this with an example. So we consider any set bit of this 3. Let's say we consider the last set bit, right? And we'll talk about how do we figure out which set bit to consider and how to find that set bit. We'll talk about that, the programming expression for that. But let's say we have an expression to find a set bit in XOR. So we consider the last set bit in the XOR. We know that the two numbers that we are going to find, one of them will have this bit as 0 and one of them will have this bit as 1. We know for sure because this is 1 in XOR, and you have 1 in XOR only when your input two numbers have different bits for this position. So what you do is you divide your all numbers into two groups such that one group has this bit set and one group does not have this bit set. So what will happen if you divide into two groups? One group that has last bit as set and one group that does not have last bit as set. So your group 1 is going to be, let's say group 1 is the group that has the last bit as set. So your group 1 is going to be 3, 3, 5, 7, 7. Right? This is your group 1. And what is your group 2? Group 2 is going to be 4, 4, 4, 4, 6. Let me just repeat what I've just done because the next thing is just one thing to do and we get the answer. So what all we have done so far is we found the XOR of all the numbers. Since there were only two odd appearing numbers, all the even appearing numbers cancelled out each other and we got the XOR of two odd appearing numbers. We took this XOR 3, we considered a set bit of this number 3. So here I've considered the last set bit, this set bit. And we know that when any bit is set in XOR, the corresponding bits in the two numbers will be different. So we divided our input numbers into two groups. One group that has the last bit as 1 and one group that has the last bit as 0. So one thing is for sure that out of these two numbers, one number will go in this group and one number will go in this group because this last bit must be different in these two numbers. Now what all we do is to find these two numbers, we do XOR of all the numbers in group 1, XOR of all the numbers in group 2 and we get the result. If you do XOR of all the numbers in group 1, what will you get? You will get 3 XOR 3, XOR 5, XOR 7, XOR 7. The 7 and 7 will cancel out each other, 3 and 3 will cancel out each other and you will get 5. If you do XOR of all the numbers in this group, all the 4s will cancel out each other and you will get 6. So you get the output as XOR of group 1 and XOR of group 2. So we get an idea. Let's now implement it. Let us now talk about implementation. So we have two variables, result 1 and result 2, which are going to be our final results. First step, as we discussed, was finding XOR of all the numbers. So we have initialized XOR as 0 and then we do XOR of all the numbers from 0 to n minus 1. And now our XOR variable has XOR of all the numbers in this array. So what it means is your XOR variable has this value 3 because when you do XOR of all the numbers, even will cancel out each other and you will have XOR of two odd appearing numbers, which is 3 here. After we find XOR of all the numbers, we find the rightmost set bit in the XOR. So this whole expression is to find rightmost set bit. I'll explain this expression separately. What it basically does, it gives you a number which has only the last bit set as your input number, right? After we find XOR of all the numbers, we find rightmost set bit in the XOR. we needed to find only one set bit, right? So we are finding rightmost set bit. Let's see how does this expression work. So our XOR is 3, whose binary representation is this. Now we find 3 minus 1 first. You can notice that we have XOR minus 1 here, which is this value. Your last bit is turned off, right? And if there were more bits after last bit, in case of 3, your last or rightmost bit itself is 1, but it might happen that there are zeros after it, right? Your last bit is probably at the last set bit probably is at the 4th, 5th position, or any position which is beyond the first position, right? So they might have been 0 in case of numbers other than 3 which do not have the last bit set. After we find 3 minus 1, we make this 1 as 0, and if there were more bits after it, we would have changed them from 0 to 1, right? That's what 3 minus 1 does. Now we find negation of 3 minus 1. This tilde operator inverts all the bits of a number. So all the bits of 3 are inverted. 0 becomes 1, 1 becomes 0, this 0 becomes 1. And if there were more 1s after it, they would have become 0 here in this tilde after applying this tilde operator. Once we have got this value, we do end of these two numbers. That's what we are doing here. That's what our final result is. And if you take a look at these two numbers, they have all the bits as different. You know, you have 0 here, you have 1 here, you have 1 here, you have 0 here, except the last set bit. The last set bit is same in both the numbers, 1 and 1, right? So you get a number as a result which has all the bits as 0 and only the last set bit is 1. That's what you get after doing this operation. I've changed the example here. I've taken two odd appearing numbers as 8 and 32 to better explain this working of this expression. So our output is 8 and 32. So what we do in this algorithm, we do XOR of all the numbers. We get XOR of 8 and 32 because all the even appearing numbers, they cancel out each other. Now we use this expression to find the rightmost set bit in this XOR. So let's do XOR of these two numbers. Binary representation of 8 is this. Binary representation of 32 is this. And XOR of these two numbers will have bit set only when the bits are different. So these two bits are different. So you will have these two bits set in the XOR. And what is decimal value of this? It's 40. So your XOR variable is going to have value 40 after this loop. Now in this 40 we need to find out last set bit. So what we do is we first do 40 minus 1. And this is the binary representation of 40 minus 1. If you take a look at this binary representation, all these bits are changed from 0 to 1. And this last set bit that we are targeting, it's turned off. And all the remaining bits are as it is. All the remaining bits are as it is. You know, all the bits at the left of last set bit. Now we do negation of this number. We invert all the set bits. Right? So we use tilde operator here to do the negation. And after doing the negation, we get all the bits inverted. So this 0 becomes 1, all the zeros, preceding zeros, they become 1. 1 becomes 0, 0 becomes 1, and this 0 becomes 1. So the last set bit is set again. And all the bits before it are inverted. And all the bits after it are again 0. So if I do end of these two numbers, XOR and negation of XOR minus 1, I can notice that these bits are inverted, so end of these bits is always going to be 0. So we are going to do end of these two. And you will have 1 for the set bit because this is set in both the numbers. And these are zeros in both the numbers. They became 1 and then again became 0. So end of these numbers is going to have this last set bit is set. So you will have many zeros and then you will have 1 and then 000. So this is what you get in this number Sn, which is a number whose only set bit is the last set bit of your original XOR. So Sn for this example is going to have this number 8, right? it's going to have only the last set bit as set and all the other bits as 0, right? So your Sn is going to be 8 here in this example. Now what we do is, we do XOR of all the numbers which have this bit set and do XOR of all the numbers which don't have this bit set, right? There is only one number that has this bit set, and that is one of your results 8. So your result 1 is going to have number 8 and result 2 is going to have XOR of all the remaining numbers, because all the remaining numbers, they do not have this bit set, which is the 4th bit from right side, which is the only bit set in this Sn, right? So we use this expression to figure out whether this bit is set or not. We do a bitwise AND. So if a number has this bit set, then you will get non-zero, otherwise you will get 0. So in result 1, you will have only 8. In result 2, you will have XOR of all the numbers. So you got one odd appearing number in result 1, and in the other set, you got all the even appearing numbers and one other odd appearing number. So these even appearing numbers, they will cancel out each other, because XOR of a number with itself is always 0, and you will get the other odd appearing number in result 2, 32. That's how you get these two odd appearing numbers.